Welcome to this lesson on electrolytic cells. In electrochemistry, we've learned about galvanic cells that produce electricity from spontaneous chemical reactions. Today, we'll explore the opposite process, using electricity to drive reactions that wouldn't occur naturally. Electrolytic cells are fascinating devices that convert electrical energy into chemical energy, allowing us to force non-spontaneous reactions to take place. An electrolytic cell is an electrochemical cell that uses electrical energy to drive a non-spontaneous redox reaction. Think of it this way. Some chemical reactions need a push to get started. These reactions have positive Gibbs free energy, meaning they won't happen on their own. An electrolytic cell provides that push by supplying electrical energy from an external power source, like a battery or direct current supply. This external energy forces the reaction to proceed in a direction it wouldn't naturally go. Let's compare two types of electrochemical cells. Galvanic cells, also called voltaic cells, work through spontaneous reactions that generate electricity. They're like batteries that power our devices. Electrolytic cells work in the opposite way. They consume electricity to drive non-spontaneous reactions. While galvanic cells convert chemical energy into electrical energy, electrolytic cells convert electrical energy into chemical energy. Both involve redox reactions, but the energy flow is reversed. Every electrolytic cell has four essential components. First, an external power source, such as a battery or direct current supply, provides the electrical energy needed to drive the reaction. Second, an electrolyte, which can be either a molten salt or an aqueous solution containing ions that can move freely. Third, the anode, which is the positive electrode where oxidation occurs and electrons are removed. Fourth, the cathode, which is the negative electrode where reduction occurs and electrons are gained. Remember, in electrolytic cells, the anode is positive and the cathode is negative. The thermodynamics of electrolysis are crucial to understanding why we need external energy. For a non-spontaneous reaction, the Gibbs free energy change, delta G standard, is greater than 0, and the standard cell potential, E standard cell, is less than 0. This means the reaction will not proceed on its own. To make it happen, we must supply external electrical energy that exceeds the positive Gibbs free energy barrier. The external voltage applied must be greater than the magnitude of the negative cell potential to force the electrons to flow in the non-spontaneous direction. Let's examine a classic example, the electrolysis of molten sodium chloride. When we melt sodium chloride and apply an external voltage, we can decompose it into its elements. At the cathode, the negative electrode sodium ions gain electrons and are reduced to form metallic sodium. The half reaction is 2 sodium ions plus 2 electrons yield 2 sodium atoms. At the anode, the positive electrode, chloride ions lose electrons and are oxidized to form chlorine gas. The half reaction is 2 chloride ions yield chlorine gas plus 2 electrons. The overall reaction is 2 sodium chloride molecules decompose into 2 sodium atoms and 1 chlorine molecule. This reaction requires significant electrical energy because it's highly non-spontaneous. Electrolytic cells have numerous important industrial applications. Electroplating uses electrolysis to coat objects with thin layers of metals like gold, silver, or chromium for protection or decoration. Metal refining, particularly of copper, uses electrolysis to purify metals to very high purity levels. Water splitting through electrolysis produces hydrogen gas and oxygen gas, with hydrogen being a promising clean fuel. Chemical production relies heavily on electrolysis. For example, the chloralkali process produces chlorine gas and sodium hydroxide, two of the most important industrial chemicals. These applications demonstrate how electrolysis is essential to modern manufacturing and technology. Let's review the key concepts about electrolytic cells. First, electrolytic cells use electrical energy to force non-spontaneous reactions to occur. Second, they require an external power source with sufficient voltage to overcome the positive Gibbs free energy of the reaction. Third, Remember the electrode assignments? The anode is positive where oxidation occurs, and the cathode is negative where reduction occurs. This is opposite to galvanic cells. Finally, electrolytic cells are essential for numerous industrial processes, including metal extraction, purification, and electroplating. Understanding electrolytic cells gives us insight into how we can harness electrical energy to perform valuable chemical transformations that wouldn't happen naturally.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.